In the last video, we started looking at the Doppler effect. Specifically, we started looking at what would happen if the source of a sound were moving towards or away from an observer. But what if instead of the source of the sound moving, this time you have an observer that's moving? So in this case, you have the source on the left, which is holding still, it's stationary, and the observer is moving toward the source. Well, you're going to have a very similar effect. If the observer moves toward the source, then he's going to hit the first wavefront, then he'll hit the second wavefront in less time than it takes the wavefront to move. So basically, in effect, he's observing a shorter wavelength and thus a higher frequency. Let me show you what this looks like here in this module. So here's the module we saw in the last video. This time we're going to deal with a source that's not moving, and we want an observer that is moving towards the source. I'm going to give it a negative velocity. That's how this computer is calculating it moving to the left. As the observer moves toward the source, the time it takes for the observer to go from one wavefront to the next is less than if the observer were stationary. And so as a result, the observer perceives a shorter wavelength and thus a higher frequency. But if the observer is moving away, then it's going to take more time because you have one wavefront that hits. Then by the time the next wavefront hits that same point, the observer's moved on. And so it's going to take more time. So it looks as if to the observer that the wavelength has actually increased, and thus the frequency would have decreased. So once again, we see another Doppler effect going on. However, the way we calculate it is going to be a little bit different. So to find the Doppler frequency based on an observer moving towards a stationary source, the computer goes through some calculations and you get this equation, or slightly simplified, you get this. Once again, this is for an observer moving toward a source. If the observer is actually moving away from the source, then that positive is replaced with a negative. The result is that here in this case, where the observer is moving toward the source, you're going to see an increased frequency. But in this case, where the observer is moving away from the source, you're going to see a decreased frequency, which is exactly what we just saw in the website just a second ago. Now, just like we did before, we took the two equations and we combined them into one by defining a positive velocity. Before, it was positive velocity when the source was moving away from the observer. Now we're going to define a positive velocity when the observer is moving away from the source. So in both cases, the velocity is positive if it's moving away from the other. And when we do that, this is the equation we get. We just have one equation. And once again, this would be, so positive velocity if it's away, but if it's moving toward, then you put in a negative velocity and you get an f prime is equal to 1 minus a negative velocity of the observer divided by speed of sound times your frequency. And because you have minus a negative, that becomes positive, gets you back to the original equation we had earlier. So that handles both if a source is moving and if an observer is moving. But what would happen if both the source and the observer are moving? Well, you would have one Doppler shift for the source moving towards or away from the observer, and you would have another Doppler shift as a result of the observer moving away or towards the source. So you have to do this Doppler shift 2 times. You have to do both a shift for the source moving and a shift for the observer moving. Now, if we combine both of these equations, then we get this equation, that the new Doppler effect frequency is going to equal the speed of sound minus the speed of the observer divided by the speed of sound plus the speed of the source, all of that multiplied by the frequency. Again, V observer and V source are both positive if they're moving away from each other, negative if moving toward each other. Is it possible for one to be positive, one to be negative? Yes. If the observer is moving away from the source, his velocity is positive. But if the source is moving toward the observer, so basically they'd both be moving in the same direction, then V source would be negative. And you could come up with all sorts of different combinations. Anyway, this is the total equation that accounts for both the velocity of the observer and the velocity of the source. And by the way, just as a note, if the observer is not moving, that term goes to 0, and you do a little bit of algebra, you get this equation back. If the source is not moving, do a little bit of algebra, you get this equation back. So this is one beautiful equation that handles all of the Doppler effect.